Good morning, everyone, and welcome to this session on putting machine learning workloads into production. I'm going to walk you through some serverless and hopefully also quite painless ways on making this happen. My name's Oliver. I'm head of machine learning at Datatonic. And in case you don't know Datatonic, we're a boutique consultancy doing all things data. We specialize on cloud technology and partner with Google Cloud Platform, where we help accelerate some of Google's largest clients in Europe and in the UK. We help from everything starting from data migration, data warehousing, building out the BI platforms, but also data science processes and machine learning. And a bit later in this session, I'm going to introduce a case study based on one of our clients where I think I can put this productionization approach of data science workloads into practice and showcase this with a real client project. So why is it so difficult to put machine learning models into production? Might not be difficult for everyone, but for me personally, the first experiences there could have been quite a struggle. My background is more academic. I come from a physics background and came through that into data science, where I joined Datatonic 3 years ago. But to answer this question, I want to illustrate a bit the machine learning life cycle as we see it at Datatonic. So when we start a data science project, we go through a series of steps, and that's usually broken up into 3 phases. We'll start with a discovery phase, that's in blue. There is a model phase, a model build part, which are the points in gray from 3 to 7. And then lastly, there's the deployment, the productionization of the machine learning pipeline, which are the last few steps here in green. But let me just briefly walk you through so we have all a similar understanding of these steps. At first, we got to define a machine learning use case. It's probably one of the most important steps to really see where machine learning can help the business, where it can provide value, and that's where you define potentially KPIs, metrics, etc. Based on that, you probably quickly go into some sort of data assessment. You want to know whether you have the right data to support the machine learning use case. And that kind of wraps up the discovery phase. Once you feel machine learning might be able to help, we got the data, can start the journey on actually building the model. And there's several steps involved with that as well. So we start with potentially some pre-selection of algorithms. Is it computer vision, NLP, regression classification at a broad level? We want to build out some of the data pipelines and feature engineering pipelines needed to support and fuel the machine learning models. That's step number 4. And that's potentially the step you spend most of the time. And often data scientists spend a lot of focus and effort on point number 4, where it's all about the data preparation and feature engineering. It might get a bit more exciting for many of us here with number 5 and 6, where you start building models and then quickly get into a mode of iterating. So you start with one hypothesis, one approach. You want to tune the parameters. You might want to tweak the algorithms, go back to the drawing board, etc. So there's some iterativeness between the steps 5 and 6, where it's really about building a machine learning model. Crucially, it's then the presentation of the results. There's no point in having many fancy models on someone's laptop or notebooks if you can't effectively link it back to the business case and show where the value lies. Is there anything machine learning can help the business with? Yes or no? The numbers should speak for themselves. And that's number 7. And it's usually the decision point where you make a call on whether to move a model into production or not. Well, let's assume we built something nice, it all works out, results are great, and we get the go-ahead to operationalization. We want to follow through steps 8, 9, and 10. And this is what I think is the hard part for many data scientists. These steps, where it's around planning and potentially building architecture and infrastructure, where it's about tying down the code, introducing logging, introducing alerting, introducing maybe some performance metrics, and also about monitoring and reliability, where you want to build highly available services and APIs. It's these 3 steps where often the skill set shows a bit gaps, where a traditional data scientist does not necessarily have the software engineering or the DevOps skill sets to really put these things into place. Just out of curiosity, who here in this room is a data scientist or machine learning expert? It's of course the majority. And who here, like myself, comes from a physical sciences or STEM background? It's probably, again, the majority of the data scientists here, or maybe half. So there's a common background with many data scientists, not coming from software engineering, but from maybe STEM or physical sciences, where steps 3 to 7 are great, right? This is the scientific process of building models based on a hypothesis, doing testing and experimentation, and that's what we're all familiar with. But these last steps might be a bit of a struggle because we don't know the right tools. One way to approach and solve this is obviously build cross-functional teams. You work together with a DevOps engineer, with a machine learning engineer, or anyone covering the skill set of productionization and make it happen as a team. Often that's not possible because of how corporations are set up, or you might be a single isolated data scientist within a business. So in the next half an hour or so, I'm going to walk you through some platforms that might help with that to enable data scientists, make this as seamless as possible, and also some more custom routes on cloud technologies to leverage serverless and make this step for operationalization as painless as possible. But let me introduce a project we've done earlier this year with a cosmetics retailer called Lush. Probably most of you are familiar with Lush. They sell these bath bombs and soaps, as seen on this picture, and they're quite successful globally. They have over 1,000 stores, operate in 50 countries. And they're on a journey to becoming more environmentally friendly, which means they want to reduce plastics and packaging in stores. So the store shelves might look a bit like on this image, and you think this is a great idea. It removes plastics, but packaging has a purpose. It displays content and information to buyers and purchasers. And this is especially important if you talk about cosmetics, because ingredients matter, right? There might be allergens, you might be sensitive. You put these products on your skin, take them in your bathtub. So having all the information needed is crucial for customers, and Lush was thinking about the way to not have packaging, but still give the product info and also things like price. So what they came up with is the idea of using everyone's phones that we all carry with us and use object detection and image recognition in an app so users can scan a product, take a picture of it, and then it will recognize the right product and pull up all the information needed. And that should work in store, but also at home. So if you buy something, you don't have the packaging, you can still find all the relevant information, including product name and price. When we started working with them, they already had a prototype built on core iOS, the built-in ML model there. And their skill set was not necessarily data scientists or machine learning. They were a team of app developers. So they were familiar with the iOS SDK, but not the data science process. The model they quickly stood up in core iOS was pretty much hit and miss. It would wrongly classify a lot, and they came to us, Lush, with 3 main asks. First, we need to up model performance. It needs to be really delivering a satisfactory user experience. The second was, because it was built on core iOS, it wouldn't work on Android. It needed to be able to be deployed cross-device and not leave out half of their customer base potentially. And lastly, they need a robust pipeline, a productionized way where they can build new machine learning models hands-off without their involvement. And this is important because Lush is very innovative. They add new products to their range on a weekly basis. So they need a process where there's new products, they can take a few images and then kickstart the whole process that delivers a machine learning model at the end of it that can recognize the newest product range. So updates thereof are very important. So let's quickly have a look at what stage we are in this process. We start talking to Lush, and luckily we already have a defined use case. Lush shared some images to train on with us as well. So we covered step 1 and 2, and what's left is let's get started on some R&D and see if we can improve the model performance. I'm going to cut right to the chase. The model we built was leveraging a deep learning architecture called MobileNet version 2. So this is a convolutional neural network. It exploits some residuals, nifty tricks to be very performant with a small footprint. So it's a small model, around 14 megabytes, geared towards mobile deployments. And we've done a lot of analysis on the images provided. We quickly realized we can up model performance a lot if we exclude, for example, images that have multiple products, if we do the cropping right, and if we introduce a large series of data augmentation steps. And this is where it gets quite interesting. You might think object and image classification is a straightforward task. Maybe people have been talking at ODSC about that 4 years ago. But the use case here is quite difficult. If you think back to how these bath bombs look like, they're all very similar. Most of them are round, they have similar textures, so there's a lot of overlap in their aesthetics. Secondly, they are all handmade. They're all handmade products, which means huge variance in uniformity in how the surface looks like. Plus, you might use them, so at home they degrade, they change shape, etc. And lastly, it needs to work as well in store, where the lighting might be very well defined and controlled, as it should work in everyone's bathroom, where the lighting might be harsh and fluorescent. So all these challenges made this a quite difficult task. We have a product range of around 200-300 products initially, and they're all quite similar. So this is not doing classification of a car versus a chair. This is distinguishing very similar type of products. So the data augmentation helped massively, especially on the color profiles and tweaking and introducing randomization on saturation to up the variance and the training set. What we then did was we used this mobile V2 architecture, which served well in early stage of this R&D, and we applied transfer learning. We used pre-trained weights on ImageNet and retrained some of the top layers. We've also changed some parts of the architecture overall. And lastly, we did extensive hyperparameter tuning. What we ended up with was a model performance gauged on the F1 score that goes from 45% to over 97%. So where the model before was really hit and miss, it would just work now and then, we delivered something with a very good usability, and the top 1 and top 3 accuracies are way above 90% as well. So this is nice, this is usable now, and it's all built on TensorFlow. So this is great. We've done this R&D period and chosen the right algorithm and tweaked this a little bit. We went back to Lush and say, hey, you know what, the model does 97% accuracy now. I think you guys are going to be happy, and they were. So we decided, all right, let's productionize this. Let's make this happen into a pipeline where the Lush web app developers can kickstart new processes to introduce new products into these machine learning models and then roll it out to their users. So now we started this phase of operationalization and this phase of thinking a bit more in terms of software development and releases. And there's a few asks around that, a few key points. And what we wanted was quickly iterate, potentially iterate over R&D again, but not for now, but allow Lush to just introduce new products, add more classes basically to the problem, and do this quickly, as continuously as possible, and basically ship now a machine learning model as they would ship a normal update to their apps. In a nutshell, they wanted as much automation as possible, because they were not data scientists, they were not ML experts, they were app developers. In software engineering, there's a whole discipline dealing with these things. It's called DevOps. It's gained a lot of popularity, and it introduced a lot of practices around exactly automation and continuous delivery. So in other words, what we want is we want to combine machine learning with DevOps, and we can coin this into a term called MLOps. It's what we call it at Datatonic, but it's also becoming much more of a term in the whole data science world as well. Not to confuse MLOps with the Microsoft library that delivers in that space, and it's just named MLOps as well. Here we're going to talk a bit in the next 20 minutes about the practice of combining DevOps approaches to data science workflows. But let me rephrase this in a few further points on why we actually need ML ops. If we build out this pipeline, we actually need to orchestrate this and run through the pipeline step by step. And potentially we need to handle multiple of them in the future as well. There could be multiple scenarios where we want to build different models. Ultimately, this needs to scale. This needs to scale to more products. This needs to scale to more performance. And in other scenarios, MLOps needs to scale to growing user bases and data. We might also want to think about having a flexible environment to improve and change modeling approaches and do experimentation. If you were going down the route on building an API, it needs to be reliable. So we think about highly available systems. And what's going to be important here, and I'm going to highlight this in a bit, is ongoing data validation and ongoing validation of model performance. Imagine you add more products, you take more images, you want to introduce them in a novel model. If you would upload very poor imagery and you would trigger model training, you need some validations, otherwise the performance might decrease. So being aware of that and making decisions based on performance and then monitoring is going to be a crucial step. And that ties in heavily with data and model governance, basically versioning. So if something goes bad, if your model doesn't deliver as well anymore to users as you'd expect it to, you want to revert, or you may want to pinpoint for regulatory reason and say, this decision came from this model. So there's a lot of questions here, and we're going to tick most of them off one by one over the next half an hour. So one approach to this would be building the cross-functional teams. As said, that's not always possible. The other approach would then go, all right, there's this whole world of DevOps. There's this whole tool set that's on this image here. Things like Docker, Kubernetes, there's Ansible, Terraform, there's a lot of CI, CD tools, artifact storage, whatnot. You can learn all of this, and you can consume it as a data scientist and become a bit of master of all of that. But what we would recommend is save a bit of your time and avoid this. And luckily, there's been massive developments in the space to build on tools to really tackle these challenges, go through this list of what we need from ML Ops, and build this into easy-to-use platforms and tools. And this field is a bit exploding as we speak, after years of heavy development and investment in machine learning frameworks like TensorFlow, scikit-learn, PyTorch, that enabled anyone to build models as easy as possible. There's now a big surge in building tools that allows anyone to deploy models as easy as possible and deliver against this MLOps practice. A few of these tools, start at the top right, MLflow, TFX, Kubeflow, they really want to provide the whole end-to-end platform for this, from experimentation to versioning to running and APIs in managed states. And some of them, like Kubeflow, runs on Kubernetes, MLflow on Spark, so they have their own execution engines as well, or leverage other open source tools. Some others in that space, like Orpheus or DVC, take a specific stance and say we want to be tools to help with data and model validation. And they take a bit of a smaller slice and just provide functionality around that. And all these tools are actually open source at this top right corner. A bit contrary to that, there's a whole range of software as a service providers, proprietary solutions that you can buy in. They're not open source, but they will be licensed under different models. There's Selden, there's Domino Data Lab, Data Robot, or Peltarion, just to name a few. There's probably quite a few more. And they want to often build a browser-based experience for data scientists to maybe drag and drop, build models, but also deliver against many of these tasks around automation and governance. Lastly, there's the main cloud providers. They all have their own utilities and tool sets. Most of them are more around deploying online APIs for machine learning services. Azure has the Machine Learning Studio, there's AWS SageMaker, and Google Cloud's AI platform that help with that as well. But this is not an exhaustive list. I just wanted to showcase a bit that now, this year, 2019, there's actually a lot happening in that space. And there's a lot of tooling already provided and a lot of solutions that can really help data scientists tackle these last 3 steps of operationalization that can be quite difficult for some data science teams. Unfortunately, not everything is quite there yet as we expect this. So after quite some experimentation at Datatonic with pretty much all of these tools, we found some limitations. And be aware, these are quite broad generalizations, but just want to highlight some maybe current issues with these platforms. There's still a bit of incompleteness, and a lot of these platforms lack some features at this minute, and that's because they're quite new, right? It's still a novel field. Also, the market fit might be explored. It also means not everything is as stable yet as we'd like to, and some of them require you to learn new APIs, new maybe bespoke languages, which obviously makes onboarding a bit harder. And lastly, especially these software as a service platforms, they threaten a little bit of vendor lock-in. The open source stack, obviously, much less so. A bit less functional, but maybe even more important, some of these require still a skill set that's beyond most data scientists around Spark, Kubernetes. And crucially, experimentation might be very much contained to these platforms, and they don't plug in very well with additional data sources or your business overall. And data science is always an experimental field. Being kind of contained there could be almost against its ethos. They also don't provide any help with breaking down data silos, and overall they focus on delivering modeling experience often, and maybe monitoring a model and helping training. But the job of a data scientist is not to build models, it's to add value to the business with data. So none of these platforms necessarily address how you can connect this to the wider business, interface with other teams, and make it as easy for a business to gain impact and acceleration through data science. But these are just some of our findings at the current stage. What I want to recommend now is, in 2019, if you're at a stage where you want to find some tooling to help deployment, check out these tools and see if they tick all your boxes. Right? If they deliver against what you need, that's amazing. Onboard them and run with it, and even if it's just a subset of your use cases. If that's not the case, don't despair. Because what I'm going to walk you through now is a very custom and tailored solution that's built on some serverless tools on Google Cloud Platform. And that's just Google Cloud Platform because we at Datatonic like this very much, but there's many other tools in the similar space that work quite keen. But I want to bring home the message that if you build on serverless and managed services, it's really not that hard to build your own custom solution to productionization. So some of the tools I'm going to introduce now that really help with all of the ask that we had from Lush to put this into easy-to-use, operationalized pipeline are things like Cloud Composer, which is managed Airflow, so that's orchestration, fully managed service. There's BigQuery as a ultimately scalable data warehouse. AI Platform is a place to run TensorFlow, but also other machine learning frameworks in managed notebooks, but also for training and deployment. And of course, we want some storage. There's object storage. And lastly, Dataflow, a managed runner to do data processing in distributed way. So remember where we were. We built a pretty decent model on MobileNet. Now we want to build a machine learning pipeline around that. There's almost like a model factory spitting out new model when needed. And we know it's a computer vision use case, so there should be some pre-processing in there. We need all the components around automation because Lush wants this as easy as possible. And again, this model validation is going to be a crucial step. We're going to look at that. And with that comes also versioning of models so we can backtrack and have some governance and audit trail of what's happening when we release new models. So when we started working on this, we kind of knew where we were going to begin with. We have training data. Over 50,000 images in this case across a few hundred products from Lush. We knew where we were going to end up with is a model that can be deployed to Android and iOS. We also actually knew that the ideal candidate in the middle to realize this is TensorFlow and its portability layer TensorFlow Lite. and we can leverage this to do cross-device deployment across different iOSs. But there were still a few gaps to fill. And besides filling out these gaps, there's some additional challenges when we talk about deploying machine learning models to mobile. There could be things like processing speed, so inference needs to be fast. Luckily, we already choose a model, this mobile net, that has a small footprint there and is geared towards inference, but we're going to apply a few more tricks to make this faster. Storage might be a limitation. The model is only 40 megabytes initially, so that's all right, but every model update, you don't want to download huge amounts of data. And lastly, we're all quite anxious about battery levels and power consumption. You don't want this app to drain your battery, right? You could also choose to deploy the model in the cloud or any other service and connect to it, but then you have problems with bandwidth, with disconnections, and even latency. So we choose to do this completely on device. So let's have the overview of the pipeline at the highest level. Again, we start from images. Straightforward way is to put this into object storage. And then there's two big blobs. One is data processing and the other machine learning. And I'm going to go into details of these two now. On the data processing side, we're going to build some first preparation steps on images in Google Cloud Storage. And the first step is converting it to TFRecords. And I'm going to tell you more what TFRecords are in a second. Once that conversion happened in Cloud Dataflow, we can split the data into training, test, evaluation sets, and store this again. And then we're going to start our data augmentation pipeline, which was coded in Tensorflow, using some of the high-level functionality there. Again, crucial step to do some randomization, some cropping, and especially play with color distribution and saturation. And this is all happening fully managed, serverless in AI platform. Well, let's talk about TFRecords for a second. Tensorflow records are its own format to store data. It's a serialized version of whatever data you can imagine and you want to deal with, and it relies on protobuffers. The nice thing here is you can actually combine training data with labels. You can also chunk up files, so having hundreds of thousands of files in remote storage, like S3 or Google Cloud Storage, can add a lot of overhead and slow down your training massively. So converting it to TFRecords, you can chunk up a lot of images into serialized files that are hundreds of megs large, which is much more optimized to deal with object storage through the throughput they have on this file size. The processing we did was actually Python pipeline, and we used Apache Beam. Apache Beam, if you're not familiar, is a processing framework that does batch and streaming with the same API. Here we did batch processing, but we used an execution engine called Cloud Dataflow in Google, and it allows you to just write Python code on your laptop. You submit it to the service, and it will automatically run the code. It will provision whatever infrastructure it feels fits the job. It will auto-scale when needed, and will tear down everything once the job is completed. So this is completely serverless, fully managed framework to run this processing. And we've done the conversion of 50K images in 10 minutes, but that includes the time to spin up infrastructure and tear down. But that's all hands-off. You don't have to deal with that. The beauty of using a managed and serverless service like Dataflow here is if you, in a few years' time, Lush has 1 million images, it works just as well. No change of code needed, and the processing time won't really increase because it can scale out massively. So let's have a look at the second big box, which is the machine learning side. And there's a few steps you want to go through here. So we have the data in TFRecords. We've done some data augmentation. Now we need to train the model. We're going to run some evaluation steps as well. And then based off these evaluation steps, we'll look at some metrics, and we store them in BigQuery. We then decide if the metrics are good enough, if a new model is satisfactory. We move on and export the model to TF-Lite, and I'll tell you more about TF-Lite in a minute. And we can do this in AI platform. And then lastly, we'll export it back to Google Cloud Storage, where the Lush developers can pick it up and bake it into Android and iOS apps and have a versioned record of that. So the training and the evaluation is again TensorFlow code, but we use AI platform, formerly known as Google's ML engine for that. And it's a nice tool because it allows to do the whole part of training, evaluation, and also hyperparameter tuning. So with AI platform, you can submit the TensorFlow code as it runs on my laptop here, and you can run it distributed across many, many nodes. You can easily attach GPUs or TPUs, even multiple ones per node. And you don't have to manage a cluster or anything. You can really scale out computations, and that's what we did here for the hyperparameter tuning. So we did extensive hyperparameter search, and AI platform even provides a Bayesian optimization algorithm. It's a bit of a black box, but it will try and optimize the hyperparameters as quickly as possible. So you can use this for scale. You can also deploy models into APIs if needed. And lastly, this is where the conversion to TensorFlow Lite happens. So after model training, we converted to TF Lite, and this is a portability layer TensorFlow built to enable models on devices. It could be phones, but it could also be a Raspberry Pi or an edge device, an IoT device, for example. And it allows some optimization to take place to really compress the model and make it as small as possible. So when we started with MobileNet, it's originally 14 megs, but we used this full integer quantization to bring this down to a quarter of that size. And there's a few more tricks that TensorFlow optimization will do in TF Lite to really optimize this. So what is this quantization? I think if you're unfamiliar with this, it's worth spending a minute or two on mentioning that. In this trained deep model, mostly convolutions, we obviously have now a trained set of weights. These are normally all stored in float 32. That's the default. So all the weights, all the activations are stored float 32. Research showed that often it's not that crucial to keep that precision, and you can actually lower the precision on inference. On training, you might want to keep full precision, but on inference, you can lower the precision to something like int 8, which is a quarter of the size of the full float, and still get almost the same accuracy. Small degradation of maybe a few % accuracy. But you can use this to really drastically reduce model size, again, by a factor of 4, which is nice. And you can also use this when you use int 8s to exploit some of the accelerators and the instruction sets of modern accelerators a lot better. So modern phone CPUs, desktop CPUs, or specific edge devices, they actually can process a lot of these int 8 operations in parallel and give you additional speed up. So what you get is a smaller model, only a few megs, and inference times that are cut in half. So we can actually get inferences on around 50 to 60 milliseconds on a modern iPhone 10 or 2019 Android smartphone. So this is nice, and the way it happens is really, you look at the whole range of floats that you have on your weights, and we want to quantize all the math here. You could only choose to quantize your weights, but we're actually also going to quantize the activation functions. And what you have to do for that is you want to scan over your weight space, maybe with your training data, and then find the min and max, have a scan there, and then apply this formula, which converts you back to the float value. But you basically map the float space onto the integer space with 256 available values. But if you also optimize the scale and you optimize your ends, you can do this mapping quite well. Of course, you lose some precision, that's clear. You also might cap everything that's beyond your max scale, so you have an Rmin and an Rmax, and you lose out beyond that. But if you do this well on the trained model, and you can even use training data to gauge these scales a bit better, you won't lose out on much precision. And what we found out in practice here with this model, when we applied full integer quantization, is we lost about 1% of top 1 accuracy. But we gained a 4-fold decrease in size and double in inference speed. So that was worth it. Okay, so we got the small model now in TF Lite. And I told you when we do the training, we'll also compare and calculate some metrics we want to judge the model on and make a decision whether this now should be deployed into mobile apps or not. And how this happens is will calculate the evaluation metrics in TensorFlow and then store them in BigQuery. So BigQuery is data warehouse from Google Cloud. It can scale to petabytes. So this here is a bit overkill, but it's a nice SQL warehouse where you can write all sorts of SQL and quickly get access to and insights to your data. And how this can really look like is we wrote rows for each run. So you have a timestamp. You might have some model parameters, number of classes, potential class references, etc. Maybe more metadata. This is just an example. And then we log things like the accuracy, the recall precision, F1, and we might make a judgment call. And we say, okay, if the F1 score is above a certain threshold, or if the F1 score didn't decrease compared to the previous run, we're going to add a flag is serving. And that's going to be true for the best model. So it's just a simple way to kind of custom build a decision engine in your ML workflow that kind of safeguards against deploying bad models. So how does this all look like in the overall architecture? You can put this together and combine the data preparation side with the machine learning side. But there's still one piece missing, and that's the orchestration piece, which will introduce a lot of the automation. So if you look all the way at the top, you see Google Cloud Composer. And Cloud Composer will run Apache Airflow as a managed service. So you don't have to create a virtual machine or anything and run Airflow. It will create it, make it available for you to build your custom workflows. If you're unfamiliar with Airflow, it's a great tool that we use a lot to orchestrate all sorts of data tasks. What it will allow you to do is write each task as in Python. So it's very expressive, very dynamic, and you can obviously version it as code. And you can then build any sort of workflows and dependencies upon that, and it provides a lot of additional functionality around monitoring and alerting and seeing how your workflows actually run. So this is a great place to do some of the automation here. And how this looks like in detail is we built each of these squares into a task in Airflow. So how does the pipeline now run is Lush will add images to Google Cloud Storage. And if they have a new product, they will make a new folder and add images there of the new product. We'll actually have a check that Airflow performs. It will look and measure, basically as a sensor, see if there's new files in Google Cloud Storage. If there are, it will count them. And only if enough images are uploaded, it will kickstart this pipeline. So once there's 30 or so more images in the bucket, Airflow will start the next step. And each step will only run when the previous one is succeeded. If there's any failure, Airflow will monitor this. It can send out emails to alert, or it can take other actions to do cleanups, etc. But now Airflow will orchestrate this whole pipeline step by step. So conversion to TFRecords in Dataflow, export to Google Cloud Storage, data augmentation in TensorFlow, followed by training. And then again, it will execute the evaluation in AI platform. And it will log the entries into BigQuery. And then Airflow will go again. It will query BigQuery and see, OK, we got the new model run. How are the metrics? How's the accuracy? It's good enough. OK, let's do the last two steps. Let's convert to TF-Lite, and let's export to Google Cloud Storage. And send out an email to Lush that the new model version is ready, or actually connect directly with their CI/CD. So this is great. The whole thing is now tied up in a pipeline where everything runs automatically. So all Lush developers have to do is, or the product team has to do is provide new images, and 20 minutes down the line, the developers will get an email that the new model in TF-Lite is ready to be baked into their mobile apps. So what have we achieved? We built a completely serverless pipeline that orchestrates all the ML tasks. It's in Google Cloud Platform, but it will work similarly well on other clouds. We leverage this TF-Lite layer to make this model available for Android and iOS. And we're also working now with Lush to see how this runs on edge devices to expand the use cases. And we also could build on the original prototype and up the performance massively. So it went from 45% F1 score to over 97. And this was originally built for 200 products, and Lush has been using this for a few months now, and it serves 500 products, and the accuracy is still over 97, I think even higher % with the same flow. So if you like Lush and you're curious about this, you can download the Lush Lens app and go to a store or use it at home and actually have a play with this. But let's link this back to what we actually wanted to achieve. In the space of productionization, we want to link this back to what we wanted to get out of MLOps. And we saw actually just using the right components on Google Cloud Platform, we didn't have to build on a novel, maybe a bit underdeveloped still, MLOps framework. We could just pick and choose the right products that are suitable for this use case. And we did orchestration in Airflow and Composer. We built something that's perfectly scalable to even hugely larger amounts of images in AI platform around training of TensorFlow models. We built a very simple logic around versioning of models and validation. We have some limited data validation happening as well. There's model governance for versioning Google Cloud Storage. And lastly, we have integration also with our GitLab. So if there's any code changes to the whole pipeline, we can test this and redeploy this as well. So everything we actually wanted to get out of this, and everything Lush wanted from a developer perspective with limited skill sets here, is actually ticked off by just a thorough selection of the right tools. And it wasn't that hard to build, even for a data scientist, because all these components are serverless and fully managed. So I don't have to deal with infrastructure and configuration files. All I have to worry about is write basically TensorFlow and processing code. So what I want you to take away from today's session is building your own custom workflow is really not that hard. There's already a great offering of tools, especially from cloud providers, to make this as seamless and as easy as possible. And some of these tools have been around for a few years and are very reliable. But this field of MLOps is very exciting. And we've had some great experiences already with some of these tools. I think there's still a lot to be said to build custom workflows. But maybe in a year's time, if I'm here again, I might give a talk about Kubeflow or any other tool, because I'm very excited about the field. And I think developments there will really mature in the next year, and we'll see much more usability coming out of these components. So that's it from my side. Thank you very much for your attention.